Okay, we just have a few pages of slides to finish off this chapter. Actually, the microphone is not working, so I just tell you myself. So, okay, so yesterday we stopped here. Here about the frustrated total internal refraction. So here, this is a table about the refraction indexes for different types of material. And you can see here on the right, on the left side, we have vacuum. It says the index is exactly 1 because if you still remember, the index of the material is the speed of light over the wave speed in that material. So and as you know, all the wave speeds in different types of materials should be strictly less than or equal to the speed of light, which means that the index must be larger or equal to 1. And for the vacuum, or for the vacuum, the index is exactly 1, and for the air, it is only a little bit more than 1, and which means that the speed of light in the air is almost the same as the speed of light in the vacuum. And probably you, when you learn this topic in high school, you also know that for the water, the index is around 1.33, and also for the glass, here, yeah, you can see the glass 1.5, or different kind of glass. I don't really know what they are, but actually you can see different material will have a different index. So yeah, so here it also include one called the diamond. So the refraction index is quite large, which is around 2.42. And that's why the lady liked the diamond, and because it can refract the light, so that the dispersion, the chromatic dispersion will be stronger for the diamond, and yeah, you will look more beautiful. Okay, so here we also talk about the polarization by refraction here. This topic probably won't be covered in high school physics. And here it says a ray of unpolarized light in the air is incident on the glass surface at the Brewster angle. So here we introduce a term called the Brewster angle. And this is different from the critical angle. This is not the same angle. So here it says the electric field along that ray have been resolved into components perpendicular to the page, and also parallel to the page. So as you can see here, this is the incident ray, and yeah, so so we have the page here. So this green arrow means the E field parallel to the page, and the orange dot means the E field perpendicular to the page. So in this case, it means that the incident ray is unpolarized. It consists of both the electric field perpendicular or parallel to the page. And if this ray is incident, displayed by the Brewster angle, theta b, then the reflected wave will be polarized, even though the refracted wave is not polarized. But actually, if it is incident with this angle, theta b, of course the refracted angle is also theta b. Doesn't really matter. And in that case, as long as the incident angle is the booster angle, the refracted wave will be polarized. So, and why it will be like this, it will be difficult to explain. Actually, when I learned it in electromagnetism, then I will need to solve the Maxwell equation and then to write the equation for the incident ray, refracted ray, and also the refracted wave. Then it will be very, very complicated to do so. But here you just memorize this fact. And yeah, so the refracted light consists only of components perpendicular to the page. So we can see here only the orange dot here, which means the E field are perpendicular to the page. So it is polarized in that direction. And the refracted light consists of original component parallel to the page and weaker component of perpendicular to the page. So this light is partially polarized. It doesn't really mean that this is perpendicular. This is not that case actually. It only means that part of the only parallel, only the E field perpendicular to the plane can be refracted, and still part of the E field perpendicular to the plane can go through this surface and then refracted by the glass. So here, this angle can be calculated by this equation. So you can see this is the glass, this is the air. So and of course the index of the air is 1, which means N1 is 1, N2 must be larger than 1. So this angle N2 over N1 is larger than 1, so arctangent of N2 over N1 should be larger than 45 degrees. And there is another interesting property is that theta B plus theta R should be 90 degrees. Should be 90 degrees. Yeah. And actually for this, yeah. So you can see here, as much as we have a N1, N1 sine theta 1, which is theta B, equals N2 sine theta R. And here, theta B equals arctangent N2 over N1, which means that if we draw a right angle triangle here, and then this is theta B, this is N2, this is N1. So this is N1 square plus N2 square and take the square root. So if we take sine of theta B, sine of theta B will be N2 over square root of N1 square plus N2 square. And then we can just substitute this term here. So we have N1, N2 over N1 square plus N2 square, take the square root on the left-hand side, and then on the right side will be N2 sine theta R. So N2 and N2 can be canceled, which means that sine of theta R should be N1 over square root of N1 square or plus N2 square. And if you look back to this figure, this is the right angle triangle. And if sine of theta R is N1 over square root of this term, which means that this one should be theta R. which means that as much as theta b equals to this value, it implies that theta b plus theta r should be 90 degrees. So this is the Brewster angle. Okay, so we still have 2 additional examples to cover to finish off this chapter. So this one is like it says unpolarized light is sent into a system of 3 polarizing sheets. The angle theta 1, theta 2, and theta 3 of the polarizing direction are measured counterclockwise from the positive direction of the y-axis. They are not shown to scale. Angle theta 1, theta 3 are fixed, but angle theta 2 can be varied. The intensity of the light emerging from sheet 3 as a function of theta 2. So the scale of the intensity axis is not indicated. So what percentage of the light initial intensity is transmitted by the system when theta 2 is 30 degree. So from this figure, you can see that when theta 2 is 0 degree or 90 degree or 180 degree, the intensity is 0. But yeah, for other value, you don't necessarily know how high it is. It is somehow like the sine wave. Of course, it is shift to 0 and positive, between the 0 and positive value. So it is not actually a sine function or cosine function. Somehow like the cosine and then 1 minus cosine, something like that. But yeah, actually we don't know the height of it. And also, it tells you that for theta 1, theta 3, we don't really know the angle for theta 1 and theta 3. What we only know is that theta 2 can be varied, which means that in order to get this figure, theta 1 and theta 3 cannot be changed. And then we try to rotate theta 2 from 0 degree, and then we try to test. From here, it is maybe you can call it I0. And then after passing through, of course, originally it should be unpolarized incident wave. And after passing through the first one, yeah, it should become the polarized ray with a certain angle. Actually, we don't really know what theta 1 is. And then we try to measure. So we can measure the incident. Probably this is I1, this is I2, so this is I3. So we can try to measure the I3, the intensity I3 here. If we make theta 2 to be 0 degree, 1 degree, so on and so forth, up to 180. And as much as, yeah, it doesn't really make sense to have 181 degree because you cannot distinguish whether it is a 1 degree or 181 degree. So from 0 to 180 degrees should be enough. Okay, so now we try to see how do we determine the angle theta 2. So first of all, the observation is that I equals 0. So let's say this is I, this is IO. We know that I equals 0 when theta 2 equals 0 degree, 90 degree, and 180 degree. So this is pretty much very clear. It means that the angle between theta 1, theta 2 should be 90 degree, or theta 2, theta 3, the angle between theta 2 and theta 3 should be 90 degree, plus or minus 90, at least we know. Because because we know that probably for this one, I1 should be 1/2 I0, and this one become polarized. And as much as this one is 0 or 0 degree, 90 degree, or 180 degree, then it means that theta 1 or theta 2 must be perpendicular to each other, or theta 2 and theta 3 must be perpendicular to each other to make this happen. So we can imagine that when I is 0, theta 1 should be perpendicular to theta 2, or theta 2 must be perpendicular to theta 3. Either one of them happen when theta 2 equals 0 degree, 90 degree, or 180 degree. So in this case, we can only make theta 1 to be let's say 0 degree, or theta 2 to be 90 degree. Of course, you can just make it like 90 degree, 180 degree, but so this should be theta 3. Because for this case, theta 1 is 0 degree. In this case, when theta 2 is 0, then theta 1 and theta 2 are not perpendicular to each other. However, theta 2 and theta 3 will be perpendicular to each other. And when theta 2 is 90 degree, it is perpendicular to theta 1, but not theta 3. So it will still satisfy this condition. And if theta 2 is 180 degree, then it is perpendicular to this one, but not this one. So we'll still get this point to be 0. Of course, you can make theta 1 to be 90 degree or theta 1 to be 0 degree, but it doesn't really change the final answer. So we can say without loss of generality. So in this case, we can try to calculate, let's say I over I0 should be, for the first stage, I1 is 1/2 I0. Now we would like to calculate the I when theta 2 is 30 degree. So now theta 2 is 30 degree, theta 1 is 0 degree. So we need to multiply by a cosine of 30 degree square. And then for the next stage, so this is the intensity at this point. And then for the final point, this is 30 degree, this is 90 degree. So we need to multiply by another cosine square of 60 degree. So actually we can, we don't have I0 here because we already derived it on the left side. So finally, this one is nothing but a 9.4%, which is the same as the previous sample problem. But based on this figure, we can actually determine the angle of the theta 1 and theta 3. And then finally, we can calculate the intensity when theta 2 is 30 degree or any other degree. Just say you can calculate when theta 2 is 45 degree or whatever. or if you have calculator, you can just calculate when theta 2 is like 41 degrees. Then. So this is about the polarization. Yeah. So here is another additional example. So here it says a certain helium neon laser, neon laser emits red light in a narrow band of wavelength centered at 632.8 nanometer. Nanometer means 10 to the minus 9th power meter, and with a wavelength width of 0.0100 nanometer. So what is the corresponding frequency width for the emission? So you may feel like this concept is a little bit strange. Usually when we talk about a sinusoidal wave, it will be like, oh, now we have the sinusoidal wave, yeah, and the wavelength is actually here. So of course, you know, C equals F lambda. So in that case, you can just calculate the F by C over lambda. You can just plug in C to be 3 times 10 to the 8th power, and then lambda to be 632.8 nanometer here, and then you can just calculate the F. And then the wave should be something like a sine of 2 pi F T, of course, plus a phi, and then multiply by a vector, something like that for the E field or for the B field, whatever. And yeah, here it mentioned a concept called the wavelength width. So it already tells you that the wavelength is 632.8. So what is the wavelength width means? Actually, in the practical world, we don't have a perfect sinusoidal. When you have a clock or oscillator, when you try to oscillate, it can be a single frequency. It will at least consist of some other B frequency. And probably you would learn some mathematics called the Fourier transform or the Laplace transform later on. And in that case, you'll be able to know that, yeah, this is a time domain waveform. You could actually transform it into the frequency domain. So we could draw it in the frequency domain. If we only have a single frequency sinusoidal, then it will be something like, suppose this one is called F0, then it should be something like, we only have the signal at f of 0, at f sub 0. We'll call it the delta function. It only exists for this frequency. So this is the ideal case, but practically, it will not be that case. It will be something like this. It will be something like this. So in terms of frequency, it will spread to some of the near frequency, which means that when we, for example, if we have a circuit to generate the clock, suppose you want it to generate a sinusoidal wave, but actually it will have something called a noise or the jitter, and then it will look like this. So that in that case, you will feel like the frequency is changing, although the period doesn't really change, but for this period, the period is actually a bit longer, and then the next period may be a little bit shorter. But overall, it turns out this variation will average out. However, in this case, when we just observe this signal in the frequency domain, it will change from this delta function to this one. and then there will be a frequency deviation. And so this is the peak. And then if we just consider half of this peak, and then we take the width here. We take the width here is called the wavelength width. It's called the wavelength width, which means that, or if we just plot it here. So this is the this should be the frequency width rather than so it is something like delta f here. So the center frequency is FO. You can just calculate it like this. However, there will be some frequency deviation. It could be very small, and also you can just plot this one in the lambda domain. So it will look like suppose this is lambda 0. Suppose this is lambda 0 rather than lambda. Then it will be something look like this. And then this is the peak. And then if we consider half of this peak, and then this width is called the wavelength width. So this is the delta lambda. So suppose this is 632.8 nanometer. And then this delta lambda is something like 0.0100 nanometer. So you can see here, this number is much larger than this one. So this is quite narrow if you just plot it in this axis. And you take the inverse of it, and then it will look like similar with a similar shape. Of course, if it is narrower, this will be wider. You may be hard to imagine what is going on right now. But actually, if you really need to calculate this number out, it will not be so difficult as much as we need to have this equation, or we can also rewrite it as F equals C over lambda. So we can take the differential, So it becomes dF equals d C over lambda. And C is a constant, so C can be factored out, and then we have d C lambda. So it will become C, and then, sorry, this one is 1 here. So if we need to take the differential for a inverse function, which is like, this is d of lambda to the -1 power. So you can apply the power rule. It becomes, you need to multiply by -1, and then this one, the power subtract by 1, which is lambda to the -2 power. In this case, we can really calculate the dF. And then of course, we still have dF for the chain, d lambda for the chain rule. So, or we can just rewrite it as -c over lambda squared d lambda. So this is just like dF, this is d lambda. Then we can just plug in the value minus 3 times 10 to the 8th power over lambda is 632.8 times 10 to the -9 power square, and then times delta lambda is 0.01 times 10 to the -9 power. So it turns out delta F will be 7.49 gigahertz. It seems like it is large, but compared with the frequency of the visible light, this is of course the visible light is the red light, then this frequency range is so small. Actually, if you think the calculus is too difficult, actually you can just consider like, oh, this is the frequency. This is a frequency f of 0, or maybe this is lambda 0. So you can consider, maybe I can draw it larger like this. So this is lambda. And then this is the delta lambda. So you can just take this one. This is lambda 0 plus 1/2 of a delta lambda. And this point is lambda 0 minus 1/2 delta lambda. So you have this point has this wavelength. This point has another wavelength. And then you can substitute these two numbers into here. So that this point is a lambda 2. This is just say lambda 1. And then you plug in here so that you have a F2. F2 to be a C over lambda 2, which will be the left point. And then if you just plug in lambda 1 to be this value into here, and then you will get F1, which will be that point. So you will have this is F2, this is F1, because they are inverse proportional to each other, which means that for the larger wavelength, you will get the lower frequency. For the shorter wavelength, you will get the higher frequency. And then you can just subtract F1 by F2. Then you will still get the delta F, which will be more or less the same with this number. Maybe not actually the same, but should be quite close to it. But if you can make use of the calculus, or at least the derivative or the differential, then you can calculate this delta easily just by this substitution. Yeah. And so this is the end of this chapter. And actually, we will still have the supplementary